On this episode of Science Max, I'm on a quest to harness the power of lightning. Its balloon-sticking, hoop-levitating, hair-raising power is all thanks to static electricity. Hold on to your grounding rods. There's electricity in the air. All on this episode of Science Max Experiments at Large. Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max, we're going to be harnessing the awesome power of lightning. How are we harnessing the power of lightning, you ask? With this balloon. I know what you're thinking. You're thinking, Phil, what's similar between a balloon and lightning? Well, nothing right now. But behold, as I use the power of static electricity and rub the balloon on my head. Because basically that's how it starts. You see, when I rub this balloon on my head, it's stealing electrons from me, creating a positive charge in my hair and a negative charge in the balloon. And the interesting thing is, you know that things with opposite charges attract each other, right? Something that has a positive charge will attract negative things and vice versa. But anything with a charge will attract anything with a neutral charge. See all these things on the table? They all have a neutral charge, which means they've got equal amounts of positive and negative. Right now, this balloon is building up a big negative charge, which means it will be attracted to all of these things. This can of Science Max soda, it has a neutral charge. The balloon has a negative charge, which means the can will be attracted to the balloon. And this paper is neutrally charged, which means the paper will be attracted to the balloon. And if you hold the negatively charged balloon next to neutrally charged sugar, haha, sugar storm. And you probably, wait, I don't want to get sugar in my hair. And you probably know this trick. If you rub a balloon on your head, you can stick it on the wall. Ha-ha! But what does any of this have to do with lightning? Well, the same thing is going on with a lightning bolt. The clouds become negatively charged, and that negative charge wants to equalize itself with the ground, which is neutrally charged. And that lightning bolt is the electricity jumping from one place to another. And you can see this yourself. If you rub a balloon on your head and you put it next to something metal, like a doorknob, there'll be a spark. But here's another thing you can do if you don't have a balloon, which I guess I don't anymore. Rub your feet, if you're wearing socks, on a carpet, and then turn out all the lights and touch a doorknob. You might be able to see a spark jump from your finger to the door. That's lightning in a very, very small form. So that's what we want to do today on Science Max Experiments at Large. Max out lightning! I think I'm gonna go to the Ontario Science Center and ask Heather her advice. She really knows her stuff. I'm gonna go see if she's busy right now. Come on.
You got the portal fixed, though.
Well, it's not exactly fixed. It's still got a couple bugs that I'm ironing out, but I stopped coming in 10 feet above the floor.
Hey.
So that's a step in the right direction. Anyway, Heather, I've come here because I want to ask your advice on something.
Yeah, for sure.
Awesome. So what I am doing is creating lightning. So this is where I'm at right now. So this is a balloon. I blow up the balloon, and then I rub it on my head, and it creates a static charge, right?
Yeah.
Just like in the lightning bolt between the clouds and the ground.
And the ground.
So I was wondering if you could help me maybe max that out, and I thought the perfect place to start would be a larger balloon.
Ooh, right on. Actually, yeah, I like this.
Yeah.
I've got a big balloon, if you just give me a second.
Sure.
All right, catch.
Okay. All right, giant balloon. So what I figured is I'll just start rubbing it on my head.
Okay.
And then we could maybe stick it to the wall or something?
Yeah, I think instead of a wall, we can even try on this whiteboard here.
Oh, okay, great.
Keep rubbing.
I'm rubbing. Okay, ready?
Yeah.
Here we go.
And...
So that didn't exactly work.
Yeah.
Both of us rubbing our heads on the balloon.
Okay.
And go. Wow, that was a whole lot of nothing.
Well, we've got a really heavy balloon here.
And I feel like our heads are only this big, so we can't cover as much surface area of the balloon.
Fortunately, you can also build up a static charge by rubbing a balloon on a sweater. Or if your balloon is giant, rubbing sweaters on your balloon. But even that didn't work so well.
I think what we need to do is come up with a better way to create a difference of charge.
Yeah, let's forget about the balloon.
You have something else?
I have something else really awesome here at the Science Center. You want to check it out?
Yeah, absolutely.
Yeah, right.
Should we take the sweater and the balloons, or should we leave them here?
We'll leave them here.
Okay.
So here's how static electricity works. Normally, everything has equal numbers of positive and negative charges. That's when things are said to have a neutral charge. But when you rub a balloon on your head, the balloon develops more negative charge than positive because it pulls electrons from your hair. The same thing happens in clouds during a storm. The cloud develops a negative charge when water molecules start bumping into each other. A lightning bolt happens when the negative charge in the cloud gets so big, the attraction to the positive charge in the ground gets strong enough that the electrons can make the jump all the way from the cloud to the ground, and you get lightning. Heather and I tried to max out the static on a balloon, but a big heavy balloon just doesn't hold the same charge.
That didn't exactly work.
Yeah.
But we're only interested in maxing out the static charge, and Heather knows just what to use.
Wow. So this is the Ontario Science Center
Yes.
electricity show.
Yes.
Okay, so where's the electricity part?
The one we're going to be playing with is right there.
So the giant mushroom.
Yeah, well, it does look like a mushroom.
We're gonna make some sort of electricity salad.
All right, head on up onto that platform right there. And I need you to put one hand on that silver ball, yes. So the way it works...
Nothing is happening.
Patience.
Okay.
Once I turn it on, when I engage it, this is going to steal your negative charge. So it's going to steal your electrons. So if it steals electrons, you're going to be positively charged.
So it'll make me more positive.
Even more positive.
Yay! Woohoo! I am positive.
Here we go.
Woo!
This machine is called a Van de Graaff generator, and it pulls the negative charge away from the person touching it.
That is great!
Instead of having equal amounts of positive and negative charges, you become positively charged.
Woohoo! Science hair! Yeah!
Like when you try to put two positive ends of magnets next to each other, each hair on your head starts to repel the others and be repelled from your head.
Science hair! Dude!
So your hair stands up.
Yes! Woohoo! I can't see anything. So this is more of a machine to generate hair standing up, but it doesn't make lightning.
Oh, well, actually, I have a demonstration in my back pocket. This is going to help us
Okay.
to create lightning. This is our grounding rod.
It is my scepter of science.
And so we're going to use this to continuously provide that negative charge.
That's why it's
static.
plugged in.
That's why it's plugged into the ground, yeah.
Okay.
Okay, so then if you touch it to that metal ball, got it? Not too exciting, right? So pull away and let's see what happens.
Whoa! This is what I'm talking about.
Very good.
The Van de Graaff creates a positive charge. The rod has a neutral charge. When the difference becomes big enough, the charge jumps the gap.
Behold, I have the power of lightning! So it's the difference between the positive and the negative is what we want when we want to make a lightning bolt.
Yes.
So is there something we can use to make that happen? Large difference of charge?
Yeah, I think I have just the thing.
Oh, yeah?
Yeah, you want to check it out?
Absolutely.
All right,
Okay, let's
do
go.
So, you would like to move electricity from here to there. Well, what you need, my friend, is a conductor. All right, a little more arpeggio this time. No, not that kind of conductor. All aboard? No, not that kind of conductor either. This kind of conductor. I know what you're thinking. You're thinking, hey, that's just a piece of metal. Well, that's right. That's because you're smart. This is a circuit. Electricity flows from this battery along the wires and into the light bulb. But Sal, you cleverly observe, the light bulb is not lit. This is true. That is because we have a gap in the circuit. And air is not a good conductor of electricity. Is metal a good conductor of electricity? Let us find out. Wahaha! Metal is a good conductor of electricity. What about wood? Nope. What about this horseshoe? Is a good conductor. Will this sandwich conduct electricity? Nope. No. What about this plastic fish? Nope. What about this pickle? No, pickle is not a good conductor. That's why we make electrical wires out of copper and not pickles. You know, in case you were wondering.
Lightning bolts make interesting patterns. That's because the electricity is searching for a way to get from one side to the other. But it's hard to see the patterns of lightning bolts because they happen so fast. Fortunately, using the power of science, we can observe these patterns for ourselves in a motion we can perceive. I'm going to use electricity to recreate a lightning bolt pattern. I've got 2 nails in a piece of wood here, and I'm going to attach electrical leads to both nails. Now, the electricity wants to go from that side to that side, but it can't. It has to go through the wood, and wood is not a very good conductor of electricity. Now, this is very dangerous. I need a special machine even to pull this off, so this is definitely not something you want to try at home. In fact, I'm gonna stand way back here when I turn it on.
Like water, electricity tries to find the easiest route to get from one place to another. But sometimes that involves branching out until the right connection is made. Lightning bolts do the same thing when they branch out between the clouds and the ground. Finally, there's a spot where the branches meet and the circuit completes itself. Then the electricity follows this one path, ignoring all the others.
And there you go. We just watched a lightning bolt happen in slow motion. Haha, science.
Back to our main experiment where Heather and I are on a quest to use static electricity to recreate a lightning bolt. Our experiments with the Van de Graaff generator had some hair-raising results, but Heather has another experiment she wants to show me.
This is Jacob's ladder.
Oh, so this is another way to make lightning.
Yes.
Lightning?
We're gonna see, yeah.
Let's do it.
All right.
How do we get it to go?
All right, so we want to turn it on.
Behold! Oh, turn it on,
Not-
okay.
not-
Go!
Oh.
Ooh, look at that!
You can actually see that light climbing up between the 2 copper wires.
That's why you call it Jacob's ladder, because it's got the rungs of the ladder.
Yeah. Between these 2 points, there's a really great charge difference, right?
Okay, so what's the difference?
10,000 volts if you're looking at it.
10,000 volts.
Yeah.
And volts is how you measure the difference in charge.
Exactly.
Why does it go up?
So it goes up because rather than just staying at the closest point, is because we're heating up the air. To a certain point,
so
yeah.
hot air rises.
Hot air rises.
And it takes the electricity with it. So if we cooled the air, it wouldn't go up?
Wouldn't immediately go up, yeah.
And there it goes, and it heats back up again.
Yeah.
That's neat. Okay, so we have a Van de Graaff generator. We got a Jacob's ladder. Are there any other devices that make lightning like this?
Ooh, yeah, there's other things like the Tesla coil, really high.
I have a Tesla coil.
You have a Tesla coil?
I do. I've got one at the lab. I've just never known how to hook it up.
Oh, I can help with that. Yeah.
Really?
Yeah.
Okay, let's do it. Let's go back to the lab.
All right. Well,
yeah. I'll turn that off. Okay.
Yeah, safety first.
Okay. By now, you're probably an expert on what happens when you rub a balloon on your head, right? The balloon becomes negatively charged, which means it will attract anything of an opposite charge, or anything positive, or anything that is neutrally charged, like, like me. Look at the hairs on my arm when I bring the balloon close. Whoa! You see, the neutral charge in my body is being attracted to the negative charge in the balloon. So if something is negatively charged, what happens if you bring something else negatively charged nearby? well, they'll repel each other. And here's an experiment you can do to make something fly using static electricity.
You'll need a balloon, a sweater, scissors, and a plastic bag out of the thinnest plastic you can find. Fold the bag up and cut off the bottom. You don't want that part. Then cut another strip from the bag. This will give you a hoop of plastic. I find it works better if you break it and tie it again. Lie it flat and rub it with the sweater. This will give it a negative charge. You'll know you've got enough of a charge when it really wants to stick to the table.
Then take your balloon and rub the sweater on the balloon to charge it up.
Because both the balloon and the hoop have negative charges, they repel each other.
Then put them together and it will repel.
And you can get the hoop to levitate.
Ha-ha, a floating bag of static charge. But here's the thing, you need to keep it away from your body, because if you get close, the bag will stick to you, because you're neutrally charged and the bag is negatively charged. Pretty cool, right? Well, let's max it out. Maxed out floating static ring. Whoa, no. Yeah! Look out, look out! Oh, no! Oh, sorry about that. Oh well. It was fun while it lasted. I gotta charge these up again.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. I didn't see you there. My name is Buster Beaker, and welcome to Cooking with Science. Let's say, for example, I've spilled the salt. Oh no, look at me. I've spilled the salt. Oh, there's salt all over the place. Not really a big deal, right? All you have to do is clean up the salt, put it back in the container. But oh no, I've also spilled pepper on the salt. But that's all right. You might be able to carefully separate the But no! Oh dear, look, the pepper and the salt are all mixed together. What do? Well, here's how you can save the day using the power of science. All you need is a cloth and a plastic spoon. Like this one here. Just rub the plastic spoon on a cloth, and you'll be charging it up with a negative charge of static electricity. If it's got a negative charge, it will attract anything that has a neutral charge, just like the salt and pepper. But I know what you're thinking. How will we separate them? Well, here's the answer, my friends. Pepper is lighter than salt. Observe. So if you hold the spoon high enough, the pepper will be attracted and make the jump up to the bottom of the spoon, but not the salt, as long as you've got it high enough up. Because the salt is heavier, you'd have to bring the spoon closer, which we're not going to do. And if you tap it off to the side, you'll make a nice little pile of pepper, and there you go, separating pepper from salt using the power of science. Thanks for watching Cooking with Science. I'm Buster Beaker.
Heather and I have been on a quest to recreate lightning using static electricity. We've gone from balloons to a Van de Graaff to a Jacob's ladder, each more lightning-y than the last. Finally, Heather suggests we use a
Tesla coil.
Oh, is this named after Nikola Tesla?
Yeah, he invented it.
Oh, one of the founding fathers of electricity, right? I
Right
love
on.
Nikola Tesla. He's cool. So how does it work?
So the way this works is it is a step-up transformer, meaning we take a lower voltage and bring it up and ramp it up to a much higher voltage.
Okay, so normal voltage is 120 volts. That's what we have a normal plug-in socket.
Typically, we're getting it out of, yeah, exactly. And we're gonna ramp that up to really high amounts, upwards of 25,000, maybe even 250,000.
Wow.
Volts.
That's a lot.
And all that charge buildup, we're gonna see something pretty amazing happen.
Okay.
Do you wanna see it?
Yes, we stand back there, right?
Let's check it out. And
The Tesla coil builds up a charge which jumps through the air to this neutral rod, just like a lightning bolt.
We made a lightning bolt! That totally jumped a long way. That was impressive.
that was a really good one.
So can you control it?
Yeah.
Okay, show me.
You wanna see? All right. I'm going to lower my frequency.
Okay.
Let's see what happens.
Oh, that's amazing. Oh, it's like a scattered lightning bolt. Oh, wait a minute, so you can play different notes?
Play different notes.
I need 5 minutes, hold on.
Okay.
Okay. All I need is 5 minutes. You know, I was thinking is if you can make different, hold that for a second. If you can make different frequencies, that means you can make different notes, right?
Right.
So I don't need that either, hold on. Ah, that's not what I need. Okay, one more thing, can I get that hammer? Yeah, okay, ready to go.
So what is this?
When you told me the Tesla coil could play different frequencies, I thought we could make different notes come out of the Tesla coil, so I programmed it to play the notes of the Science Max theme song.
What?
Yeah! You wanna hear?
Yeah.
Let's try it. Yeah! Science Max, experiments at large, lightning bolts!
Speed lightning!
We have created lightning! Woohoo! Lightning dance!
This episode of Science Max Experiments at Large is all about light and bending light to your will.
Huh? Right?
And challenges me to an ever more tricky game of light manipulation. Plus lasers, periscopes, and what does that have to do with light?
Cut to animation!
Find out on Science Max Experiments at Large.
Greetings, Science Maximites. I'm Phil, and today on Science Max Experiments at Large, we're gonna be looking at light. Okay. Stay. That wasn't supposed to happen. I was supposed to press that button, and there were supposed to be all these lasers and special effects, but it didn't. Well, today on Science Max Experiments at Large, we're not gonna be doing one experiment, we're gonna be doing a number of small experiments because we are going to do a light manipulation challenge. I'm gonna get an expert and she's going to challenge me to a game of light manipulation because I am the master of light. Oh, well, at least the green lights are working. And okay, forget it. I'm just gonna turn it back to normal. Come on, back to. I'm gonna work on that later. I'm gonna need an expert to help me though. Oh, I know, Anne would be really good at this. It really does look kind of weird in here, doesn't it? Oh, well.
You okay?
Hi.
Hi,
Anne.
Phil.
Yeah, I couldn't see what I was doing. Here's your lab coat.
Oh.
Thank you for coming.
Great.
Now, you're from Let's Talk Science, right?
Yes, that's right.
All about science education, just like us. Now, you're gonna challenge me to a light manipulation game?
A light manipulation game. I've been working on a series of challenges since last time we talked. Each
Awesome.
a little more difficult than the last.
Well, this is gonna be great, because I am the light manipulation master.
Okay, well, we'll see about that.
Okay.
Challenge number 1.
Take a seat.
Oh, well, that's easy enough.
I have written something on the back side of this ball.
Okay.
And I'm going to challenge you to read it.
Okay, well, I'm ready. I might be able to read it from here. Let's see.
All right.
Okay, I see something's written on it, but I can't read what it says.
What if you squint?
It looks like a couple lines, maybe? I can't quite tell.
Any ideas how to solve this challenge, Phil?
And I have to be in this chair?
Well, you can get out of the chair to set up your solution. But
Okay.
when you read what I've written on the ball, you have to be sitting in the chair.
Well, it's light manipulation, right?
Mm-hmm.
So, wait a minute, I've got flashlights in case the power goes out, so maybe I can use a flashlight. Haha, okay, ready? Pew! Doesn't seem to make it any easier to read. Yeah, I got nothing.
Did you give up already?
No, of course I don't give up.
I told you these were going to be challenging.
This is nothing. I will figure this out. I don't know yet.
You're going to have to get creative.
I don't know yet, but I will think of something.
Okay.
Okay, I will be back. Here, hold the flashlight. Not looking, not looking. I'm gonna go this way.
I'm going to wait right here.
Okay. Have you ever wondered why you end up upside down when you look at yourself in a spoon? It's because of light reflection. Light is made of photons. Let's say that these tennis balls bouncing off this wall are photons of light. Now, when the surface is flat, like a mirror, the photons, they bounce in and straight back out again. But when the surface is curved, the photons don't go straight out, they get reflected. So now, this photon is going over there, and if we had photons on this side, they would... I don't even know where those ones are coming from. Then, okay, so we got photons on this side that are going that way, and photons on that side that are going this way. So the top becomes the bottom, and the bottom becomes the top, and that's why you look upside down when you look at yourself in a spoon. Okay, cut to animation, cut to animation!
A lens works by changing the direction of light, too. Lenses are made out of curved pieces of glass. When the photons of light pass through the glass, the curved surface makes their paths change. What was only this big before becomes this big when you see it. Lenses are used in microscopes to see things that are really small, or in telescopes to see things that are very far away. Both times they are making something small appear large. Anne has challenged me to figure out how to see a small object far away, and using a lens is my solution.
Check it out. It's a giant magnifying lens, and I'm gonna use it to magnify the ball so that I can see it.
Sounds great.
All right.
I set the lens in front of the ball, which Anne has turned so I can't see what's on it. I add a light,
Shine it on the ball so that it's a little bit better illuminated.
and then sit in the chair and ask Anne to move it so it's aligned.
All right, so bring it to your left. Yeah, keep going, keep going. Keep going, right about there. Try bringing it closer to the ball. Okay, wait, that makes it smaller. Try bring the lens away from the ball. Ooh, wait. Try a little bit further. Ooh, ho, ho, ho.
You're ready for me to spin the ball around?
Yep.
Okay.
It says 71.
Nicely done.
Easy. Solved.
Wait.
What?
That was just the warm-up.
Oh, yeah?
Yep. You ready for challenge number 2?
Challenge number 2!
I've got another ball.
Okay.
With something else written on it.
Wait. Are you coming back?
Nope.
Huh. But I can't even see you from here. Like how am I? Huh.
You're gonna have to manipulate the light.
I have to see around a corner? I have to see around a corner. All right. I'll think of something. So you remember the tennis balls in the wall, right? Okay, so the tennis balls are photons, what light is made out of, and the wall is a mirror. Now, right now, the photons are hitting the mirror and bouncing directly back. But what happens if they come in at an angle? Like this. Aha! Those photons are reflecting off the mirror and going that way, which means if I want to see what's emitting those photons, I can see it from here. The same thing happens when you look in a mirror. Oh, okay, mirror. Whoa. The mirror reflects the photons over here. I can see the tennis ball launcher in the mirror, which means if there was a barrier, between me and the tennis ball launcher, I can still use a mirror, and the photons would reflect off the mirror and it comes straight to me, which is how you can use a mirror to see around a corner. In fact, periscopes work the same way. Let's make a periscope right now. Hey, it's dark in here. Oh, right, because I'm gonna show you my laser. So the light from my laser bounces off this mirror in a straight line. Haha, reflection. We can use the power of reflection to make the light go where we want it to. We're gonna build a periscope.
Submarines use periscopes because it's hard to see when you're underwater. A submarine will extend a periscope up above the water. The image up here gets transmitted down here. So someone looking through the periscope underwater can see what's going on up on the surface.
And here's what you need to build it. 2 cartons of milk, 2 small hand mirrors, scissors or a craft knife, a pencil, and science tape, which is the same as regular tape, except you use it for science. And remember, if I go too fast, you can always find these instructions on our website. Step 1, cut the tops off your milk cartons.
Take your mirror and trace out a rectangle as wide as the mirror, then cut it out. Put some science tape on your mirror and stick it in the carton at an angle. Then put a piece of tape on the inside. Then,
Get the other milk carton and do the same thing. Put a mirror on the inside and then stack the milk cartons together. But don't stack them with the holes on the same side. Make sure you stack them with the holes on opposite sides. And here is what's going on inside. You've got your two mirrors, and one is angled like that, and the other one is angled like this. Light from what you're looking at comes in, hits that first mirror, goes down to that second mirror, and goes to your eye. You can use it to spy on people from below the table. Or from around corners. So there you go, your very own Periscope using light reflection. Did you know that your TV remote can be a flashlight? It's true. If you have the kind of TV remote with a little bulb on the end of it, then when you press the buttons, the bulb lights up. Yeah, I know what you're thinking. You're thinking, Phil, wait a minute, the bulb did not light up, and I've never seen the bulb on my TV remote light up when I press the buttons. Well, that's because your TV remote works on infrared, which is a kind of light you can't see, but you might be able to see it with a camera. If you have a digital camera or a camera on your phone, now you can see, It lights up. And because infrared light works the same way as visible light, in that it will bounce off a mirror, here's an experiment you can do at home. Bounce the light off your TV remote off a mirror and turn on and off your television. Check this out. You get a mirror, set it up just right, and then aim the remote at the mirror, and it turns off the television. Pretty cool, right? But now, let's max it out. I've got a complex series of mirrors set up here, and I'm gonna bounce the light from the remote all over the room. And here's what that pattern looks like.
the light from the remote hits this mirror, which reflects to this mirror, which reflects to this mirror, and then this mirror, and then this mirror, and then finally to the television.
Isn't that cool? There you go. Maxed out remote light bouncing infrared flashlight. I gotta come up with a better name, but still, it's pretty cool. Oh, right. Turn off the television and leave the room.
I solved Anne's first light challenge, seeing something far away, with a lens.
It says 71!
But now she's moved the ball around a corner, and now I have the solution.
Mirror! A mirror will let me see around the corner.
Clever.
Right? Okay, so all I gotta do is put the mirror in a position sort of like that, I guess, and then I'm gonna sit in the chair. If you could help me adjust that mirror. Keep going that way. Keep going, keep going. Yeah, stop. Nice, okay, go ahead and flip the ball around and I will read the message. It is too small. I can't, okay, I've solved this problem though. Okay, flip it around. The lens, I need the lens. So we'll use a mirror and the lens to, good. Yeah, okay. I'm gonna sit in the chair. You're in the chair. It is backwards. Oh yeah, a mirror inverts the image, doesn't it? Mm-hmm. That's okay, I can solve this. All I need, whoa! Other mirror is all I need to solve this problem. So if I take this mirror and I put it here, let's see, there it is. It says 42.
Nicely done.
I
Nicely
am
done.
ready for anything. What do you got planned for the hardest challenge?
Are you sure you're ready for this?
Totally.
Challenge number 3.
Challenge number 3 starts now.
What? Wait. No. This is a light challenge. How am I supposed to do a light challenge if it's dark?
You have to get creative.
but it's dark. Well, okay, no problem. I will think of something. I will be back.
Okay.
Okay, careful.
I'll be waiting. Careful.
So you already know about reflection, right? That's when the beam of light, say from my laser, reflects off this mirror and bounces in a straight line. But check this out. If I don't use the mirror and I shine the laser against the underside of the water, it also reflects, just like a mirror. This is called internal reflection. If I have a stream of water and I put my laser beam into the stream, you can see that the laser bounces around inside the stream of water. It's being internally reflected, and the laser isn't going straight anymore. It's following the stream of water down where the water goes. Internal reflection. Now I know what you're thinking. You're thinking, Phil, how does this affect me in my everyday life? Internal reflection. Who cares? Well, I can tell you why you should care in 2 words. Fiber optic wires. 3 words, fiber optic wires. You see, fiber optics carry information all over the planet. The internet, maybe even your television, travels through fiber optic wires. The good thing is, because of internal reflection, you can bend fiber optic wires any which way or around corners, and the beams of light continue to go straight down inside the wires and get out the other end, making it go where you want it to go. Internal reflection, science.
Back to our light challenge. I've seen something small from far away, seen around corners, but now Anne has turned off the lights. But I have a solution.
Ann? Ann?
Careful.
Okay. Sorry, I forgot how dark it was in here. Okay, I figured it out.
Okay.
I have a flashlight.
No.
So all I need to do-
No. Hold on.
What?
There's one more rule I didn't tell you.
What's the rule?
You can't use visible light.
How in the world am I gonna do this if I can't use visible light?
It's a challenge.
Wait a minute. Okay, here, I'll hold my flashlight for a second. I'm gonna make a phone call.
Okay.
I think I know what to do. I'll be back. I'll be
Okay.
back.
Oh, careful. Oh.
Oh, hey, good to see you. Speaking of seeing things, let's talk about the rainbow. All the colors of the spectrum organized in a beautiful pattern. But what are the different colors? I mean, what makes them different? Well, it all has to do with the electromagnetic spectrum. This is visible light. All the colors of the rainbow. And take a look at that little black line that goes up and down there. That's the frequency of the light. Light is a wave. You see the wavelength is a little wider out here on the red side, and it's a little closer together here on the violet side? That's because every color of light has a different length of wave or wavelength. And that is what makes them different when we look at them. But if you think that's all there is to the electromagnetic spectrum, then you're mistaken. So what happens over here on the red side? Does it keep going? Yeah, it does. What? Look, we got infrared here, and then we got microwaves. These are the same kind of waves you use in your oven. And then we got radio waves, which are the same kind of waves you use in your radio. They're all part of the same thing as visible light, huh? Let's take a look at the other end. Remember these short wavelengths over here beside violet? Well, does that keep going? Yeah, if they keep getting shorter, you get ultraviolet, and then X-rays, and then gamma rays, huh? Pretty amazing. And look, it's all connected. From radio waves to gamma rays to visible light in between, it's all frequencies of electromagnetic radiation. How is it staying up? So everything outside of the visible spectrum is invisible, right? Wrong! Ha-ha! Bam! Huh?
That is an X-ray, a picture we can take using this part of the spectrum.
we can use special cameras to see outside of the visible spectrum. Huh? Huh? Right? Yeah. Okay, you got it. Huh? And look at these. These are night vision goggles. They help you see in the dark. They use part of the spectrum called infrared.
For those of you keeping score, that's this part of the spectrum right here.
Pretty neat, right? I would sell you these, but they're already spoken for. Oh, and here he comes now.
Hey, Sal.
Hey, how you doing?
You got those goggles I ordered?
Yeah, go ahead, help yourself.
Thanks for putting them aside. Can I put them on my tab?
Yeah, no problem.
All right, thanks, Sal.
Okay, see you later. Nice kid. He's always in a rush, though.
Phil, is that you?
Yeah,
Do you need the flashlight?
I don't. Turn it off. I can totally make my way over to you. Oh.
I can hear you.
Yeah, I'm right here.
Oh.
Right here.
Hi.
Because I have night vision goggles. Ooh, check it out.
Oh, cool.
Pretty cool, right?
That's awesome.
So here's the spectrum again, and here's visible light. My night vision goggles use infrared, this part of the spectrum here with wavelengths just a little bit longer than the red we can see.
Outside of the visible light spectrum.
All right, I would say that's allowed.
No visible light, and I will see the next ball. Have you got it set up?
I set it up while you were out.
Okay, good. I'm gonna sit in the chair and see if I can see it.
Okay, here we go.
Oh wow, I can totally see everything.
Can you tell me what the ball says?
It says you win.
Nicely done.
So let's recap. This challenge is the same as the last challenge. The light from the ball was magnified by the lens, sent around a corner by reflecting it off a mirror, and flipped back around by using another mirror. But this time it's dark. So, using infrared light, thanks to my night vision goggles, I was able to see the ball and win the game.
The light manipulation challenge is done. Science Max experiments at large. Time to turn the lights back on.
Yep, absolutely.
Huh.
What did you do back there?
I guess we blew a fuse or something.
Uh-oh.
Today on Science Max, it's all about gas pressure. Low pressure, high pressure, good ideas,
A nucleation fountain.
and bad ones.
Let's carbonate pickle juice.
All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Today we're using fizzy drinks in our experiments. And a fizzy drink is just water with bubbles of carbon dioxide gas dissolved in it. So I thought since we exhale carbon dioxide, I could make a fizzy drink by just blowing bubbles in this water. Doesn't seem to be working though, does it? I don't see any bubbles, do you? No. Water does absorb carbon dioxide gas, but I don't have a fizzy drink. Weird. Time to check the book of science. Oh, in order to make bubbles, you have to have pressure. So... This is an air compressor. It takes air and compresses it, puts it under pressure. So... The container needs to be pressurized. Okay. When you get a container of a fizzy drink, the carbon dioxide gas is put in there under pressure, and it stays in there under pressure until you release it. That's the sound of the pressure being released. And when it is released, the carbon dioxide gas starts to expand. And when it expands, it creates bubbles. And that's what makes your fizzy drink. This process takes a while to run out, but eventually it will become flat. No more bubbles. But what if there was a way to release all of that carbonation all in one go? Well, there is. And for this experiment, all you need is your favorite brand of fizzy drink, Science Max brand Diet Science Cola, 100% science, 0 calories. And your favorite candy, like these Science Experiments. All the minty flavor that comes from pure science. So, all you need to do is open this up, take one of these, and put it in here with an adult's permission because it can get kind of messy. Whoa! What's going on here is all of the carbonation that was in the bottle is now being released much more rapidly than it would have been before. Now, why does this happen? Well,
If you look at a carbonated beverage, you'll see that the bubbles don't come from everywhere. They come from the inside of the glass, or in this case, a lot are coming from the straw. And that's because the carbon dioxide bubbles like to find a little imperfection, something to hold on to in order to expand and bubble out. And a candy, such as this, has a ton of little tiny microscopic imperfections. So when you drop it in, there's a lot more places for the bubbles to attach, and that makes the carbonation happen a lot quicker. But remember, this is not a chemical reaction. It all has to do with carbonation. So that's what we're gonna be looking at today. Air pressure, more pressure, less pressure, and of course, we're gonna be maxing out this experiment. All right, I just need an expert to help me max this out. Let's see, oh, Cynthia from the Ontario Science Center. She'd be perfect for this. All right, good. Okay, come on, let's go. And, yep, that's good. Oh, hey, Cynthia!
Hey, Phil, how's it
Cynthia
going?
from the Ontario Science Center, you're gonna help me max out the science experiments and diet science cola experiment. I think we need a better name for this.
Okay, well, we have the mints that have tiny little pores called nucleation sites on them. The gas inside the cola is gonna go through these nucleation sites, create a giant fountain. So why don't we call it a nucleation fountain?
Ooh, Nucleation Fountain, I like that. It's accurate and it sounds awesome.
There we go.
Okay, so we wanna max it out. So how many should we put in?
Let's say 5 more nucleation sites.
More reaction. Ah. I tried adding more mints, but one at a time didn't work. It doesn't,
No.
it's not, the bubbles are pushing it back out again. There we go, there we go. And then, yeah, I think if we put them all in at the same time, it would work better. So we came up with a delivery mechanism to get all the mints in at the same time. A tube with a magnet holding the mints up, which we screw onto the top of the bottle. Pull the outside magnet to release, and... Oh, nice.
Oh, yeah.
Oh, yeah.
That's a good fountain.
That is a
good nucleation fountain.
Nucleation fountain worked very well.
There we go.
Cynthia and I decided to try some other ideas to max it out even more. We decided to do some
Experimentation.
experimentation.
Oh, that's a good one. Yep.
And see if Diet Cola was the best carbonated drink to use. We tried 4 different kinds: Diet Cola, regular cola, lemon lime soda, and club soda.
Really just
It's just carbonated water.
carbonated water.
3, 2, 1, go. Science cola, but I think that it was close.
I think it was the release.
Let's watch the replay.
Okay.
Yep, Diet Science Cola went the highest.
So the next step is
Maybe if we want to max the size of the fountain, we have to make a narrower stream.
ooh, so a smaller aperture opening will be higher pressure
That's what I'm thinking.
because it'll be forced at a smaller opening. What else can we do?
We can launch it.
We could launch. Oh, you mean like sideways?
Yeah.
Yeah, I love that idea. So we'll put it on wheels. We'll put it on wheels.
Okay.
And then we'll launch it sideways.
Okay.
We got a lot of things to do. Okay, let's get.
We need time. Let's do it.
Get to it. Okay, we'll go to
Okay.
the lab. I'll get a mop. Nothing like a fizzy glass of water. And now there are ways for you to carbonate water at home with something like this, the Science Max Carbonation Station. You have a bottle of compressed carbon dioxide gas that's hooked up.
You take a bottle of tap water, attach it, and carbonate it.
Voila! Carbonated water. But this is Science Max. Why just carbonate water? Let's carbonate everything! Let's carbonate pickle juice. It's actually amazing. Milk! It's like milk meets water, kind of very odd. Chocolate milk? Oh no, that's way better. Carbonated mustard. Carbonated tomato juice, carbonated hot sauce. No, wait, carbonated
That was the hot sauce. No. Carbonated clam chowder. Oh, there you go. Carbonation. Not just for water anymore. It's definitely not for clam chowder. No, that's just a big bowl of no. Never again.
Cynthia and I are maxing out a nucleation fountain.
Yeah,
Oh,
that's a good fountain.
We're changing our design a bit to see if a smaller hole in the bottle cap will make for a higher pressure fountain, which will make it more maxed out.
We have this large hole. We've got a medium-sized hole.
We have a very small hole
So we're gonna see large, medium, or small, which one is the best.
to max out our fountain.
Exactly.
But the problem is that our old delivery mechanism won't work if we keep the cap on. So we needed to come up with a new delivery system. So we drilled holes in the mints and put them underneath the cap on a pipe cleaner. They hang at the top of the bottle until we pull the pipe cleaner, and then they fall in.
All right, are you ready?
Oh, I'm so excited. Which one do you predict will be the best? This will have a larger geyser.
I
These
think
ones
this
be
will
smaller.
look cooler
Yeah.
because it'll be big, but this one?
The smallest hole, I think, will go the highest.
Yeah, ready?
Three,
two, one.
Definitely the biggest.
There. Whoa, careful, careful, careful. Whoa.
This one is almost like a spray.
It's not like a mist.
Yeah,
it's a mist of cola. They all kind of worked a little differently. The interesting thing is this one lasts the longest.
Oh.
There we go. So, this was cool, but not the best.
This one's still going.
It's still going.
It's not over yet.
You gotta give it points for still going.
I think this fountain looked the best, though.
This one was pretty good. So, a small aperture, but maybe not the smallest aperture, would be the best. So because of the force coming out of here, I think that we could probably do something like putting it on wheels.
And shooting it like a rocket?
Yeah, let's see.
On wheels?
Or like a car.
Oh.
Yeah, we'll make a nucleation fountain car. The Nucleation One!
It's our race car.
It's our race car. It's got fancy wheels that spin really well.
And we decided to go with the medium aperture. So it's fairly big, but not too small.
Yeah, all we need to do is unscrew that, put that in there, and then pull it out.
Three, two, one. Oh, good. Let it go. Oh, that's not so bad.
Oh, yeah!
Missed the finish line.
Past the thing! Turn it around, turn it around!
Did we make it get to the finish line?
There, it's
No.
spinning out.
Oh, wow.
Go! There.
It worked pretty well, but there's always more ways to max it out.
What if we just got like a giant container? Like, because we're using small containers, right? What if we just
So
got a
you
really
want
large
to carbonate
container?
a very large container.
Well, we'd have to figure out some way to, well, come on, let's go figure it out.
Okay, let's do it.
This is an egg. It's been hard-boiled and peeled, so there's no shell on it. This is a flask, and this is hot water. I pour the hot water into the flask, which means the air inside the flask starts to heat up. And when it heats up, it expands, and some escapes through the top of the bottle. I pour the water out, and then I cap the flask with the egg. Now this expanded air is starting to cool again, which means it's lower pressure, which means the higher pressure on the outside of the flask pushes the egg in. Ha-ha! Fun! And then, to get the egg out, I can reverse it. If I blow into the flask, I can increase the pressure inside. Science! And now let's max it out. Max out container! Okay, pour out the water. Oh, careful, careful. And now, I put this water balloon on the top, and we'll just see what happens. The hot, expanded air inside the container is cooling and reducing in pressure, which means the higher pressure outside the container,
It's happening!
pushes the balloon in.
It's happening! Oh. Success!
maxed out. Did you know that we live on the bottom of an ocean of air? It's called the atmosphere. And compared to the Earth, it's really thin. I mean, it's about as thin as this. Huh? Look at that, not very thick at all. But it's a good thing the atmosphere is around, and not just for breathing. Though I am a fan of breathing. What do we want? Breathing! When do we want it? All the time. But did you know the atmosphere has different layers? It's true. I will walk you through them. No, I mean, come on, you gotta come with me. I'm walking over to walk you through them. Okay, the troposphere. This is the layer where we are all existing right now, where all of our weather happens. There's a lot of air molecules in this layer. Think of these balloons as air molecules. There's a lot of air in this layer. Yay, air! Next layer, the stratosphere. There's less air molecules in this layer, and it's where jets fly. Next layer, the mesosphere. There's even fewer air molecules in here, and it's where meteors burn up and turn into shooting stars. Fire, 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 fire! Whoa. The thermosphere. Not many air molecules left up here, and this is where the northern lights, the auroras, happen. Woo! Northern lights. And finally, the exosphere. This is as high as the atmosphere goes. This is where satellites orbit, and if you see any air molecules up here, they're just passing through. Hello. And after that, nothing but the vacuum of space. Ooh, the vacuum of space. Of course, you know it's not that kind of vacuum, right? Right. Vacuum just means no air. There you go. The atmosphere. The only thing separating us from the vacuum of space. Roberta, the space vacuum got broken. I don't know how.
Cynthia and I are maxing out the Nucleation Fountain.
This one is almost like a spray.
It's like a mist.
Yeah,
it's a mist of cola. Just to experiment, we tried using a giant bottle and pouring the Diet Cola in. I'm a little concerned about the science, but it didn't work.
Well, that's not very exciting.
Okay, so that didn't work at all.
No,
This is not a chemical reaction.
it's a physical change.
So it's the carbonation that matters.
Exactly.
When we poured the cola into the bottle, we lost almost all the carbonation.
How are we gonna max it out?
That's the question. So if we can't make a larger container,
More bottles?
we just have more bottles. So we'll just get a
Exactly.
lot of them and we'll set them off in a sequence or something.
Okay, let's do a pattern or something. We'll max out the
I know what we
fountain.
should do. You know, we should be sort of like a cascade and we'll get a lazy Susan or This is a vacuum chamber. It's an airtight container, and I put a hose on it, and the hose is attached to a pump. Now, the pump takes the air out of the chamber, creating a vacuum. So, let's have some fun putting things in a vacuum chamber. Marshmallows in a vacuum chamber. The marshmallows grow larger, whoa, then shrink much smaller when returned to normal pressure. Why? Well, take a look at what happens with this balloon. The vacuum takes the air and the pressure out of the container, which was pushing against the sides of the balloon. Without that outside pressure, the air molecules inside the balloon can expand. So let's max it out with maxed out marshmallow. Just like the balloon, the marshmallows expand. But unlike the balloon, the air in the marshmallows escapes, so they shrink when the pressure is added back in.
They're almost the size of regular marshmallows.
It's the air inside a marshmallow that makes it fluffy.
It's not very fluffy.
The same expanding process happens with marshmallow cookies
The marshmallow has completely deflated and it's all kind of hollow inside.
The frosting on a cake?
More cake! No, no! Oh! Look at this giant birthday cake. I can't wait to eat it. No! No! Why birthday cake?
And even shaving cream.
No! Shaving slime.
Cynthia and I have done a whole bunch of different experiments
Experiments.
to find out how to max out the Nucleation Fountain.
So we'll just get a lot of them and we'll set them off in a sequence or something.
Okay, let's do a pattern or something.
Now we have a bunch of bottles and we're ready to try the maxed out version.
We've got our release mechanism.
With our medium aperture.
Yep, and we're gonna put the mints in all of the bottles and then we're gonna release them in a very coordinated,
Pattern.
rehearsed pattern.
Very rehearsed.
We've rehearsed it a couple times. We'll see how it goes. And we've got this lazy Susan, which will spin around and we'll see how it goes. And 3,
2, 1. 1,
2,
3,
4,
5,
6,
7. Surprise! 1, 2, oh, go, 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 3, 4. We did it!
Whoa!
It's raining Diet Science Cola. We maxed it out!
Maxed out! Nucleation Fountain. That is as good as it's gonna get.
So let's recap. Our Nucleation Fountain is all about releasing the carbonation in our Diet Cola faster than normal. This happens because there's lots of tiny bumps on the mints for the carbon dioxide to grab onto and make bubbles.
High fives. There you go. Science Max, experiments at large, Nucleation Fountain. Excellent job. Now all we need to do is clean it
Clean
up.
up, and I think I need a shower with water.
Yeah, I think I need at least the towel.
Yeah,
Okay,
But it's supposed to volumize your hair.
Is it good for
I
your
think
hair?
So.
I
Yeah,
hope so.
better than
'cause-
honey and things like that.